On today's installment of Physics with Mr. G, we'll be talking about power and springs. This will be the last podcast for the 5th unit, power and springs. First, we're going to talk about power. So here's a crappy little Honda. It has a mass of about 1,100 kilograms, and it accelerates from 0 to 60 in 7.2 seconds. Here's a sweet McLaren F1. It has the same mass, but it accelerates from 0 to 60 in only 2.6 seconds. So which engine does more work? So using the conservation of energy, we know that the work done by the engine is the same in both cases. Because we know that the initial energy plus the work equals the final energy, our work energy theorem. And the initial energy is 0, because we're talking about kinetic here, and it's not moving to begin with. So work just equals 1/2 mv squared, and the velocity is the same for both, so you get the same work for both. And because the masses are both the same, you get the same amount of work done. So there we go, carried out. It's about 15,800 joules or 15.8 kilojoules for each of the cars. So what's the difference? Why would anybody pay a crap load more money for a McLaren F1 when they can get the same amount of energy out of a Honda? Well, that is easy to answer, because the F1 is more fun to drive because it has more power. It is more powerful than your little rice-burning Honda Accords. So what is the formula for power? Why are fast cars, or more powerful cars, more fun to drive? So power equals the amount of work divided by the time. So once you find the work, you just divide by the time. It's that simple. So that little Honda Civic accelerates real slow. The F1 accelerates real fast. So what is the power of the Honda Civic, and what's the power of the F1? We're going to show you. So we already said that the amount of work done is about 15,800 joules. So power equals work divided by time. Final velocity 60 miles per hour. So we need to convert that to meters per second. We don't like miles per hour in physics. We got to convert that to meters per second. If you can't remember how to do that, you should probably practice, because I guarantee I'm going to give you that on a quiz. So you take that 15,800 joules, you divide it by the 7.2 seconds, and you get 2,194 joules per second. The F1, you do the same thing, except for you're dividing it by 2.6 instead of 7.2, and you get 6,077 joules per second. So almost 3 times, well, maybe not quite, maybe 2.5 times as powerful as the Honda Accord. So that's why you pay more money for your F1s and your Lamborghinis and your Jaguars and stuff like that. More power. It's like Tim the Toolman Taylor. You guys are probably too young to remember that, though. So there's a special name for a joules per second, so we don't always have to write J over S. We call this a watt. So power equals work divided by time, so the units are joules per second, which are watts. So just like Newton stands for kilograms meters over second squared, and a joule is a kilogram meter squared over second squared, a watt is a joule per second. You can also call that a joule, or a kilogram times meter squared over seconds cubed in SI units. Kilograms times meters squared over seconds squared would be a joule, or we're going to divide it by another second, so it's seconds cubed. So that's a watt. So think of a 60-watt light bulb. Your standard light bulbs in your house. It uses 60 joules every second that it's burning. So we're going to wrap up energy. So far we've talked about work. We've talked about kinetic energy. We've talked about potential energy. We've talked about the conservation of energy. And we talked about power. There are other types of energy. In kinetic, there's also rotational kinetic energy, which we're going to talk about in a couple units. And for potential energy, there are springs, chemical. You have your electrical potential energies, which we'll definitely talk about. There's nuclear. There's light. And there's heat. So we might cover rotational kinetic energy. But we're definitely going to cover springs right now. And we're going to cover electricity in a couple months. We are definitely going to cover light and heat as well. Maybe nuclear if we fly through this stuff. So now we're going to talk about springs. So springs pull harder the further you stretch them. Think of a slinky. You pull it out, you let it go, it's going to come back faster if you pull it back. Well, if you pull it back too far, it's going to stretch out into a wire. But a spring, if you stretch it out really far and you let it go, it's going to come back a lot faster than if you stretch it out a little bit and let it go. So here's how you find the force due to a spring. F equals negative kx. That k, that's a new little thing, is the spring constant. And x is the distance from equilibrium, how far the spring is stretched or compressed. You might also see it as negative k delta x. So equilibrium is how a spring looks when it's just sitting there. If we stretch it out, it's going to be stretched out. So how much it's stretched out is your delta x. Or it could also be compressed. So how much it's compressed is also your delta x. And that k is going to have units of newtons over a meter, newtons per meter. So this is a very special formula in physics. It's called Hooke's law. F equals negative kx is known as Hooke's law. So example, what is a force applied by a spring with a spring constant of 10 newtons per meter when it is stretched 30 centimeters? So we're looking for force. And then we know that equals negative kx. So negative 10 newtons per meter times 30 centimeters, which we have to convert that to meters. So it's 0.30 meters. So you get a force of negative 3 newtons. So this negative sign means that spring is going to come, it's going to move backwards. It's going to compress after you let it go. If it ends up being positive, like the spring's compressed, your distance is going to be negative. That means it's going to spring out whenever you let that spring go. Yeah. Let me clear that. Here. So negative 3 newtons, just like I said. All right, so now we're stretching a spring. So this little distance in here is our delta x. So what's the force now? So force equals negative kx, which is negative 200 newtons per meter times negative 0.11 meters. So you get a force of, bring out your calculator, negative 200 times negative 0.11, 22. I should have known that, duh. I need a calculator for that one. Come on, Mr. G. The 22 newtons. That's positive. When it's compressed, you're going to have a positive force. When it's stretched, you're going to have a negative force. So the energy stored up in a spring is the integral of the force over the distance. If you're not in calculus, don't worry. I'm just going to show you what that equation looks like to get the energy from that force equation. So you may take as the given that the potential energy is 1/2 kx squared. So this is spring potential energy. So how we get that for you calculus people? Integral of negative kx dx. So that becomes 1/2 kx squared plus the c, which we don't have to worry about. So an example, box 5 kilograms on a frictionless table compresses a spring with a constant of 20 newtons per meter, a distance of 20 centimeters. After the spring is released, what is the velocity of the box? So all these still do with conservation of energy. So the potential energy initial, kinetic energy initial, potential energy final, kinetic energy final. It's going to be the same on both sides. And since we don't have any kinetic to begin with, that's 0. We don't have any potential at the end, so that's 0. So we're just left with the initial potential energy, which in this case is the spring potential energy, equals the final kinetic energy, which is 1/2 mv squared. So we plug in our numbers, and you solve for v, and you get 0.6 meters per second. So here's a neat little example if you have a trampoline in your backyard. So if I have 3 feet of room underneath my trampoline, and the trampoline has a spring constant of 2,000 newtons per meter, how high can I jump on my trampoline before I have to worry about hitting the ground underneath? And then we're also going to do it for your 70 kilogram friend. So my mass is about 90 kgs. So we're going to do the conservation of energy. My potential energy, initial plus kinetic energy, initial equals potential energy, final plus kinetic energy, final. So here we have a trampoline we're going to jump on. You're going to want to find how high you are if this is 3 feet. How high you can jump before you hit the ground. So this one's kind of weird. You have, what can we cross off on these sides? Obviously, we can cross off the kinetic energy. But on this one, do we cross off potential or kinetic? We want to know this height. So we're going to be some distance above this trampoline. So therefore, it's going to be all gravitational potential energy. So our potential energy on the left-hand side is our spring potential energy, 1/2 kx squared. Our potential energy on the other side is mgh. Now, it gives us this unit in feet. We don't like feet, we like meters, so we got to convert that. And there's 3.28 feet in 1 meter. So that gives us 0.915 meters. Alright, so we're solving this for h. That's easy to rearrange. Just gotta divide both sides by mg. So we get kx squared over 2mg. So k, yeah, I know what my k is. I can just erase that. So we'll plug in my numbers here. My k is 2,000 newtons per meter. My distance that's compressed is 0.915 meters. That's squared over 2 times my mass of 90 kgs times gravity, which is 9.8 meters per second squared. And you plug this in your calculator, and you get a height of 0.949 meters. Okay, so this is how high above the trampoline I am. I want to know how high above the ground I am. So this is height of the trampoline. I want to know height above the ground. So it's at 0.949 plus how high the trampoline is from the ground. So that's 0.915 meters. So my height above the ground is going to be 0.949 plus 0.915, 1.864 meters. Oop. Forgot to click on my pen again. So 1.8 something meters. So that's how high above the ground you can jump on your trampoline. Now to do it for the 70 kilogram person, all you gotta do is replace this 90 with a 70, and you get a height of 1.22 meters above the trampoline, and you get a height of above the ground for the 70, it's 1.22 plus your 9.915. And that's going to be, let's see if I can do this without a calculator, 5.312. 2.135 meters. So a lighter person can bounce higher, and fat people like me, we can't bounce as high. That's it. Hope you've enjoyed.